Welcome to Paper Simplified, a podcast brought to you by SILMA AI. Today we're doing a deep dive into a technical report um,
Okay.
called Command A, an enterprise-ready large language model by Cohere.
Sounds interesting.
So our goal in this deep dive is to really get under the hood and understand what makes Command A tick.
Hmm.
Especially from, like a technical perspective, we'll be like exploring its architecture, training process, the capabilities that it boasts,
Right.
all based primarily on this technical report. For you, the learner, we aim to kind of provide a clear and thorough understanding of this new model, what's innovative about it, and how it's designed for those crucial enterprise applications
Okay.
without getting lost in like overly academic language. So let's get started by unpacking the pre-training phase.
All right. So pre-training is the essential first step,
Hmm.
where Command A learns the fundamental patterns of language, from a massive data set of unlabeled text.
Huge amount of data.
Right. Think of it as the model building its foundational understanding of grammar, vocabulary, and how words relate to each other, simply by being exposed to a vast amount of text.
Yeah.
This is achieved through self-supervised learning, where the model essentially predicts the next word in a sequence. This initial stage lays the groundwork for the model's versatile language understanding.
I see. So like the scale and the variety of data that they use for this pre-training, it sounds pretty impressive.
It's quite comprehensive. Command A was trained on a multilingual data set, spanning 23 languages critical for global business.
Wow.
So their data sources are diverse, including, the usual public web text and code, which you see in many large language models.
Yeah.
However, they also incorporated internally generated synthetic data sets, human-annotated instruction tuning data sets, and even high-quality proprietary data from specialized vendors. So this blend of sources is designed to create a well-rounded and robust language model.
So it wasn't just about like scraping everything they could find online. What steps do they take to kind of ensure the quality of that web-based data?
Right, that's a crucial point. They implemented a rigorous process to optimize the web text. They actively increased the representation of educational content,
That makes sense.
right, which is logical for building a strong base of knowledge. They also employed machine learning filters to identify and downsample content deemed low quality.
Uh-huh.
This filtering happened after an initial deduplication stage and the application of their own safety and quality heuristics. So it was a multi-stage cleaning and selection process.
A very thoughtful approach to curating their training data. And how do they determine the right balance, like between all these different data sources in the final mix?
That's a good question. Through careful experimentation, using ablation studies with smaller versions of their models. This allowed them to test different data combinations and see which ones yielded the best performance on relevant metrics. It's an empirical method to really fine-tune the impact of their training data.
Makes sense. Now let's move on to the core of the model, its architecture. What's particularly noteworthy there?
So Command A utilizes what they describe as a novel hybrid architecture. The key innovation here is the way they balance efficiency and high performance. A significant aspect is the use of parallel transformer blocks. This allows for improved throughput, meaning the model can process information more quickly,
Hmm.
without compromising its overall accuracy or capabilities. Think of it like having multiple lanes on a highway, allowing more traffic to flow smoothly.
Faster processing without sacrificing performance. It's always a desirable combination.
Always, yeah.
Anything else stand out about the architectural design?
Yeah, a couple of interesting choices. Similar to Google's PaLM model, they opted not to include bias terms in their neural network. While this might seem like a minor detail, it can actually contribute to greater training stability, especially when you're dealing with models of this immense scale. It helps to prevent the model from becoming overly sensitive to small fluctuations during training.
So it helps maintain a more consistent learning process at scale.
Precisely. The other architectural element that I found particularly clever is their decision to share the input and output embedding matrices. Given the massive vocabularies of these large language models, this sharing significantly reduces the memory footprint of the model. And what's remarkable is that their experiments showed no noticeable performance degradation as a result of this memory-saving technique. It's an efficient way to manage resources without impacting the model's capabilities.
A really smart optimization. With the data and architecture in place, how do they approach the actual pre-training process in terms of fine-tuning?
Their approach to optimizing the pre-training process was quite efficient. Instead of conducting extensive hyperparameter tuning on their final largest models, which would be incredibly computationally expensive,
Huh?
they primarily performed these optimizations on much smaller scale models. They employed techniques known as mu-P and mu-transfer, which are sophisticated methods for effectively transferring optimal hyperparameter settings from smaller models to larger ones. While they did still perform some targeted sweeps for each specific model size, to account for variations at different scales, the majority of the optimization was done more efficiently on smaller versions.
Scaling up the learning from smaller experiments,
Hmm.
a resourceful way to manage computational costs.
Right.
Now, pre-training these enormous models requires substantial distributed computing infrastructure.
Absolutely. All of Command A's models were trained on a powerful cluster of NVIDIA H100 GPUs, utilizing their own internal JAX-based distributed training framework. This framework leverages JAX's GSPMD to implement highly sophisticated sharding strategies. Essentially, they divide their available GPUs into a multidimensional grid to optimize how the massive amounts of data and the model's parameters are distributed across them for parallel processing.
Sharding is so crucial for handling the sheer size of these models.
Absolutely.
What specific parallelism strategies did they employ to kind of maximize efficiency?
They utilized a combination of different parallelism techniques, each designed to address specific bottlenecks in distributed training.
Yeah.
First, there's data parallelism, or DP, where the training data is split across the GPUs, and each GPU processes a different subset of the data. Then there's fully sharded data parallelism, FSDP, which goes a step further, by not only sharding the data, but also the model's internal states across the GPUs, reducing the memory footprint on each individual card. And then for even larger models, they employed sequence parallelism, or
What's the
SC.
one parallelism? That sounds more intricate.
It is more complex. But the fundamental idea is to shard the activations, the intermediate data being processed by the model along the sequence length of the input, specifically within the attention mechanism after the initial QKV projection, query, key value. They shard the data along the heads dimension. To minimize the communication needed during the attention calculations, the outputs of the attention layer are sharded on their outer dimension, and the weight matrix of the final attention transformation is sharded along its contracting dimension, a technique similar to what's used in the Megatron framework. The goal here is to minimize the amount of data that needs to be transferred between the GPUs during these computationally intensive operations.
So it's all about strategically dividing the workload
Right.
to reduce that inter-GPU communication, which can be a major bottleneck.
Precisely. By carefully sharding the activations and weights, they aim to keep as much computation as possible local to each GPU, minimizing the need to send data back and forth. For instance, in their feed-forward network block, FFN, their SP setup requires no communication of activations at all. They even manage to overlap the computation of the FFN's expansion layer with the communication required for the attention activations. And similarly, for the reduced scatter operation after the attention and the FFN's reduction, these are clever engineering optimizations to maximize efficiency at this scale.
And what about other components of the model, like layer normalization and the embedding layers? How are they handled in this distributed training scheme?
Those operations, layer normalization and the embeddings, are independent along the sequence axis. This means that in their sequence parallelism strategy, they don't incur any communication overhead between GPUs. It's all about identifying which parts of the model can be processed independently and which require communication, and then designing the parallelism strategy to minimize that communication where it's most critical.
I read that they even managed to overlap the communication of weights for one layer with the computation of the previous one.
Yes, they optimize the training loop by unrolling it in a way that allows the communication of the weights for the upcoming layer to happen concurrently with the execution of the current layer. This pipelining of communication and computation further improves the overall training speed.
And they utilize those specialized Hopper FP8 tensor cores on the NVIDIA GPUs to further boost throughput.
They did indeed. While some research has indicated potential instability with very long training runs at FP8 precision, Cohere reported that they did not observe such issues and instead saw improved throughput by leveraging these cores. However, they adopted a cautious approach. They maintained the main model weights and optimizer states in FP32 for greater precision and stability, but cast the model weights to BF16 or FP8 just before they were used in the actual computations.
So they're using the lower precision formats for speed during computation.
Right.
but retaining higher precision for the core parameters and updates.
Exactly. They also kept computationally sensitive operations like exponentials, softmax functions, layer norms, and the output embeddings in FP32. The attention computations, however, were performed in BF16. Interestingly, they also conducted a small number of initial training steps using BF16 precision. This was a deliberate choice to mitigate potential downstream performance degradation that they had observed could occur if the entire training process was conducted solely in FP8. It's a very nuanced and carefully considered approach to harnessing the benefits of these advanced hardware capabilities.
Okay, that gives us like a good understanding of the intensive pre-training phase. Let's now turn our attention to post-training. This is where they refine the model for specific tasks and improve its alignment, correct?
That's right. And this is where Command A employs a particularly innovative and decentralized strategy. Instead of the more traditional sequential fine-tuning of a single base model, they used an approach that alternates between centralized fine-tuning of a core model and decentralized training of multiple expert models, each specializing in a specific domain or capability. Following this, they merged the parameters of these expert models to create a single, versatile model.
Decentralized training followed by merging. It's a significant departure from conventional methods. What were the specific substages involved in this post-training process?
It was a multi-stage process designed to build specific capabilities and then integrate them. It started with the training of an instruct model. This involved initial supervised fine-tuning on a base model, using a broad range of instruction-following data to establish fundamental conversational abilities. Next came the SFT expert models phase. Here, they trained 6 distinct expert models, each on a carefully curated and specialized data mixture, designed to maximize performance in specific areas such as code generation, multilingual tasks, logical reasoning, retrieval augmented generation, tool use via APIs, and ensuring safety.
6 specialized experts, each honed for a particular domain.
Right.
What was the next step after training these experts?
The next step was to combine the knowledge of these experts. They used various parameter merging techniques to take the 6 independently trained expert models and merge their parameters together, resulting in a single aggregate model they called the SFT soup model.
Okay.
After this merging stage, they further refined the SFT soup model using reinforcement learning, or RL techniques. This RL fine-tuning aimed to better align the model's behavior and responses with human preferences, leading to the RL soup model.
So the soup models are the result of blending these specialized experts. And the final stage was the polishing.
Yes, the final stage was the creation of the polished Command A model. This involved further refining the model's output, particularly its writing style and overall quality. They used a combination of best-of-end supervised training on high-quality data and an interesting iterative optimization approach they termed ping-pong. This ping-pong method alternated between offline preference learning and online reinforcement learning until human evaluators indicated that the model's output quality had reached a plateau.
That ping-pong approach sounds quite sophisticated. Let's delve a bit more into the reinforcement learning techniques they employed for alignment.
So they utilized both direct alignment through preference training and optimization based on reward signals, obtained via reinforcement learning. These reward signals could come from a learned reward model that predicts human preferences, or from verifiable metrics like the results of unit tests for code generation, or the correctness of answers in reasoning tasks. They employed various preference training methods, including SLIC, DPO, and IPO.
And the novel self-refining robust preference optimization, or SRPO, that they developed. What's the core idea behind that?
SRPO is a key innovation in their alignment process. Unlike traditional preference training methods, SRPO is formulated as a min-max optimization problem. The goal is to learn a policy that can generate improved outputs while ensuring it doesn't deviate too drastically from a reference model. What's particularly noteworthy is its robustness. It's less sensitive to the specific way the preference dataset is sampled, which can improve its ability to generalize. Additionally, SRPO enables a unique capability. At inference time, the model can iteratively refine its own output through multiple passes, leading to progressively better results.
That ability for self-refinement at inference time could be a significant advantage. What about their approach to optimizing the reward model itself using RL?
For that, they employed a contrastive policy gradient approach, known as COPG. This method uses a KL-regularized RL objective, which means it not only tries to maximize the reward, but also penalizes the learned policy for deviating too much from a prior policy. The loss function is based on the rewards of multiple possible completions and the divergence of the policy from a reference. CoPG can be used both offline, on static datasets, and online, where the policy is updated based on new interactions. Its gradient has the form of an off policy gradient, but without the complexities of importance sampling or needing a separate value network. Importantly, it comes with theoretical guarantees for estimating the optimal policy, even when used offline. They primarily used CoPG in both offline and online on-policy settings.
And their internal reward model demonstrated strong performance on those industry benchmarks, reward bench and RMB, didn't it?
Yes, it achieved very high scores on both of those benchmarks, indicating a strong capability to accurately assess the quality and alignment of the model's generated text.
Let's now discuss the specific capabilities that Command A exhibits. Instruction following is a fundamental one,
Right.
as you mentioned earlier. How do they ensure strong performance in this area?
They built robust instruction following capabilities through a combination of supervised fine tuning, SFT, and offline preference tuning. Their data collection process involved generating synthetic prompts and then having human annotators evaluate and refine the model's responses. They also utilized an iterative reward-based sample refinement loop where their internal reward models would score generated completions, and the best scoring ones would be used to create improved SFT and preference training data in subsequent iterations. They found that their SRPO method was particularly effective for achieving a high-performing final instruct model.
It makes sense that a strong ability to follow instructions is the foundation upon which other capabilities are built.
Absolutely.
What about more complex abilities like retrieval augmented generation, tool use, and acting as agents?
These are crucial for enabling LLMs to tackle real-world enterprise tasks. Command A was trained to strategically leverage external knowledge through Array and interact with external tools via APIs to handle complex tasks and automate workflows. Their training data for this included user prompts, descriptions of available tools, step-by-step reasoning processes, examples of tool calls and their outputs, and the final model responses complete with citations when using Array. This data was meticulously annotated by trained internal annotators using a React-style approach, which involves alternating between reasoning and acting, i.e. calling tools. They employed multiple review stages and majority voting to ensure the quality of the preference data. They also generated synthetic interaction trajectories, which were then verified by other LLMs.
So they're not just teaching the model to use tools, but to think through the process of when and how to use them effectively within a larger task.
Precisely.
Multilingual support is another critical aspect for enterprise adoption on a global scale.
Absolutely. Command A supports an impressive 23 languages that are significant for global business operations. Their data mixture for multilingual learning, used in both SFT and offline preference tuning, covered a wide array of tasks including machine translation, safety evaluations, logical reasoning, controllability, RAG, and agentic behaviors, all across these multiple languages. They source data through human annotation, leveraging multilingual data arbitrage opportunities, utilizing templated public datasets, and employing machine translation techniques. They also used a multilingual best-of-n approach, where they would generate multiple responses from different expert models for challenging multilingual prompts, score them, and use the highest quality responses for further training.
That best of N strategy sounds like a clever way to harness the diverse strengths of their expert models for multilingual applications. And coding ability is obviously a key requirement for many enterprise use cases.
Definitely. Their focus in code was on 8 priority programming languages and 5 SQL dialects, with the goal achieving strong performance in code generation, translation between languages, and code optimization. Their training data incorporated execution feedback, natural language explanations of code, paraphrased code snippets, stack traces, database context, diff patches, and unit testing requirements. They placed a high priority on data where the generated code passed execution-based validation. They even implemented execution-based code data enrichment during the pre-training phase. In the reinforcement learning stage, they optimized for both code correctness, as measured by passing unit tests, and for annotated preferences, related to code style, documentation, and formatting. Their approach to training the code expert involved a 2-stage supervised learning process, with a secondary fine-tuning
Integration is absolutely essential for ensuring reliability. What about the model's reasoning capabilities?
For reasoning, their supervised fine-tuning relied on synthetic mathematical reasoning datasets that were rigorously filtered by other LLMs to ensure their correctness. For preference tuning and reasoning tasks, they used either preferences rated by human evaluators or fully synthetic pairs of correct and incorrect solutions. They found that the correctness of the solution was a particularly critical factor in guiding the preference training for reasoning. Their model merging strategy prioritized initially merging the reasoning tuned expert with the instruction tuned base model, as this was found to be a good indicator for which experts would merge, well, more broadly.
A very targeted and validation-focused approach to developing reasoning abilities. And with the increasing importance of processing large documents and conversations, long context handling is becoming a crucial capability.
Yes, for enhancing long context handling, they synthetically generated examples by sampling long sequences from their pre-training data and then prompting their command R plus refresh model to create question-answer pairs based on these long contexts up to a length of 8,192 tokens. They then used their reward model to select the highest quality generations to ensure the training data for long context was effective.
And finally, the critical aspect of safety.
Right.
How do they address the potential harms and biases in such a powerful model?
Safety was a paramount concern throughout the development process. They implemented a two-stage filtering process during pre-training to remove potentially harmful content, specifically focusing on CSEA, child sexual exploitation material, and sexually explicit content, as well as generally low-quality text. In the post-training phase, they utilized both supervised fine-tuning and preference data sets that included manual and automated labels, identifying safe and unsafe content. A key focus was on achieving a balance between preventing harmful outputs, limiting under-refusal, and ensuring the model doesn't refuse to answer legitimate queries, limiting over-refusal. To achieve this, they split their safety-related data sets into components designed to either increase safety or maintain helpfulness. They found that offline preference tuning was particularly effective for limiting over-refusal. While SFT was more efficient for increasing safety, their dedicated safety expert model combined an offline preference loss with an equally weighted supervised fine-tuning loss during its training. They also considered enterprise-specific safety aspects such as controllability, the ability to condition the model's safety behavior based on different instructions, and demographic fairness. Assessing the model's robustness to demographic variations in tasks like resume summarization.
That comprehensive approach to safety, covering both general harms and enterprise-specific considerations like controllability and fairness, is really important for responsible AI deployment. Now let's revisit that model merging process. Can you elaborate on how it actually works at a technical level?
Model merging essentially involves taking the trained parameters, the weights and biases, of multiple different models and combining them to create a single new model. The specific mathematical operation used to combine these parameters can range from a simple averaging of the corresponding weights in each model to more complex weighted averages or even more sophisticated techniques. The goal of merging here was to integrate the specialized capabilities of their independently trained expert models into one unified model, avoiding the need to run multiple models or use complex routing mechanisms at inference time.
They mentioned several types of merging, including expert merging, Polyak averaging, seed merging, and interpolation.
Right.
Could you briefly explain each of those in this context?
Certainly. So, expert merging, as we've discussed, is the process of combining models that have been trained for different specialized tasks or domains. Polyak averaging involves averaging the model's parameters across different checkpoints during a single training run. This can help to smooth out the optimization process and often leads to a more robust final model. Seed merging involves combining models that were trained with different random initializations, different seeds. This can improve the overall robustness and generalization of the model by averaging out the effects of any particular random initialization. Finally, interpolation can be used to recover certain capabilities that might have been diminished during the training of a specialized expert model. This might involve merging the expert model with the original, more general base model at a specific ratio.
But for combining their 6 capability-specific experts
Mhm.
to the soup model, they primarily relied on linear merging, a straightforward averaging of the weights.
That's correct. They found that a simple linear averaging of the weights, often with manually tuned weights for each expert, proved to be surprisingly effective. While they did experiment with more complex merging methods, they didn't observe significant enough performance gains to justify the increased complexity and computational cost. Linear merging also has the practical benefit of being associative. which simplified the management of their multi-stage training pipeline and made the results more interpretable.
And they found that prioritizing consistency between the expert models was more important for a successful merge than the absolute peak performance of each individual expert.
Exactly. Because all of their expert models were initialized from the same base instruction following model and shared certain core architectural components like the handling of special tokens and long context. Maintaining consistency across these models was crucial. This consistency helped to prevent negative interactions or collisions when their parameters were averaged. They even included a small amount of cross-domain data in the training of each expert to further enhance their compatibility for merging.
It sounds like the merging process itself is relatively computationally inexpensive, but the real bottleneck is evaluating the performance of the resulting merged model across all the different capabilities.
Precisely. While the act of averaging the weights is quick, thoroughly assessing the performance of each merged model across their wide range of capabilities and relevant evaluation metrics requires significant time and computational resources. This evaluation bottleneck actually influenced some of their decisions regarding merging strategies and the design of their expert training processes.
And the final polishing stage was essential to refine the merged model further. What did that involve specifically?
The polishing phase was the final step in their post-training process, aimed at addressing any artifacts that might have arisen from the merging of the expert models, and to further align the model's output with human preferences, particularly in terms of writing style, tone, and overall quality. This involved several techniques. First, they performed supervised fine-tuning on a carefully selected subset of their highest quality data, using a best-of-n sampling approach guided by their reward model to select the most preferred outputs. Then they conducted offline preference tuning using human evaluations. Finally, they employed online reinforcement learning from human feedback, RLHF, using their COPY-G method. The ping pong strategy they used, interleaving offline and online preference learning, proved particularly effective in improving alignment and maintaining training stability during this final phase. Polishing often led to significant improvements in human preference scores and could recover or even enhance performance in areas where it might have slightly regressed after the merging stage.
So that final polishing is crucial for ensuring the model not only performs well on benchmarks, but also produces outputs that are aligned with human expectations and preferences in real-world use. We've covered a tremendous amount of technical detail in our deep dive today.
We certainly have. Command A represents a very sophisticated and thoughtfully engineered large language model with a number of intriguing technical innovations in its development process.
Okay, let's bring it all together with a quick summary of the key takeaways and the novel aspects of Command A that have really stood out as we've explored this technical report.
Certainly. Key takeaways include Command A's strong emphasis on being enterprise ready, evidenced by its development of robust agentic capabilities, like tool use and RAC. Its impressive multilingual performance across 23 languages is another significant achievement, as are its competitive abilities in code generation, including support for languages like COBOL, and of course their novel self-refining robust preference optimization (SRPO) technique for alignment is a notable contribution.
The hybrid parallelism strategies they implemented for efficient distributed training, along with their careful management of FPA precision to maintain stability, are definitely noteworthy technical choices that highlight their engineering prowess.
Absolutely. Their decentralized post-training approach, involving the training and subsequent merging of specialized expert models, presents a unique and potentially very effective way to combine diverse capabilities into a single efficient model. The fact that they achieved largely preserved expert performance through relatively simple linear merging is also quite remarkable.
And the substantial improvements they observed during that final polishing phase really underscore the critical importance of aligning these powerful models with human preferences to ensure their practical utility and safety. The extensive evaluation results detailed in their report further demonstrate Command A's competitive performance against other leading models, while maintaining a focus on efficiency.
Beyond SRPO and the decentralized training pipeline, some other novel aspects of Command A include their specific attention to enterprise-relevant capabilities and their explicit consideration of safety aspects, such as controllability and demographic fairness, which are not always thoroughly addressed in broader evaluations of LLMs.
So this deep dive provides a valuable look into the cutting edge of large language model development, particularly for those critical enterprise applications. For you, the learner, we hope this has offered a solid understanding of the technical foundations and the exciting potential of models like Command A, What specific aspects of its architecture or training process sparked your curiosity the most? What real-world enterprise challenges do you envision a model with these capabilities being uniquely suited to address? These are the kinds of questions that further exploration into the fascinating world of large language models can help us answer.